Hello, my name is Radek Erban and I am a professor of mathematics at the University of Oxford. This YouTube channel is dedicated to a course I've been teaching here in Oxford. The course title is Stochastic Modeling of Biological Processes. It is taken by students of mathematics. The lecture notes for this course are published by the Cambridge University Press as this textbook called Stochastic Modeling of Reaction Diffusion Processes. In Oxford, we have used chapters of this book as lecture notes of courses ranging from undergraduate to graduate levels. The videos on this YouTube channel were prepared for the most basic of these courses, which means that more advanced topics from the lecture notes will be omitted. There is also another very good resource supporting your learning on this website, where you can find computer codes which compute all illustrative simulations and figures presented in the lecture notes. In Oxford, students taking this course have already had some basic courses on differential equations and probability. They can also attend an optional course on deterministic modeling of biological processes, covering models written in terms of differential equations. In fact, this is one possible way how we can teach mathematical biology at university level, dividing the curriculum into deterministic and stochastic modeling. Here, deterministic means in some way predictable. We know the future for sure, while stochastic is random. We cannot predict the future for sure. In this introductory lecture, which I will call Lecture 0, we will discuss some motivating examples. I will use these examples to show that the boundary between these two approaches is actually quite blurred. In fact, deterministic models can appear to be quite stochastic, and stochastic models can give rise to deterministic behavior. My first motivating example is not covered in the lecture notes. It is not a biological one, but it can provide some nice insights into questions and concepts studied in this course. My first example is the Galton board, which is named after Francis Galton, who used it to demonstrate the bell curve. It is a very simple device, which I am demonstrating in this video. Taking a ball, it goes down and hit pins on its way. At the end, the ball is collected in one of these blue columns. I can repeat this experiment multiple times with different balls, and you can see that it is quite random. So I could start thinking about designing a suitable stochastic model describing my Galton board. The basic model is that there is a 50% chance to go left and a 50% chance to go right at each pin. This can be simulated on a computer using its random number generator, and I am demonstrating a result of such a simulation in a video generated by this stochastic model. At each pin, we flip a coin and there is a 50% chance to go left and a 50% chance to go right. Each ball is then collected in one of these containers. I will simulate 10 balls and I will obtain the following result, considering as my observable the numbers of balls in each container. Simulating 10 balls, I obtain the following result, 0, 2, 3, 4, 1, 0. This is obviously a stochastic random model. So if I repeat the same simulation, I will obtain a different result. For example, 1, 0, 4, 3, 1, 1. The resulting distribution of 10 particles looks quite unpredictable. However, simulating 10,000 balls, we always obtain the following distribution of particles, with 3% of balls landing in the first container, 16% in the second container, and 31% in the middle container. In particular, stochastic models can give rise to deterministic, predictive behavior provided that we simulate many realizations of the stochastic process and report its average behavior. In this course, we will be interested how the average behavior can be estimated, not only by running many stochastic simulations, but also analytically, which is possible for simple models by analyzing suitable equations. This is certainly possible for the model of the Galton board, as I am illustrating here. On the first pin, 50% of the particles go to the left and 50% go to the right. At the next level, we have three possible positions with distributions 25%, 50%, and 25%. Continuing in the same way to the last layer, we observe that we obtain a binomial distribution of particles. There are 5 layers, 5 decisions to be made. To end up in the k compartment, we need to turn k times to the right, so the binomial number 5 over k gives us the number of paths to end up in the corresponding compartment, and we divide it by the total number of paths, which is 2 to power 5. The derived binomial distribution gives us the same results as we previously reported using a computer simulation. In particular, there was actually no need to do computer simulations for this specific example of a stochastic model, because we could derive the same information by analyzing the underlying stochastic model. This will also be the case of some simple stochastic models of biological systems, which we will discuss in our lectures. Our teaching philosophy is that it is still useful for students to implement such models on a computer because they will be able to test the correctness of their computer codes by comparing their computed results with the known analytical results. Considering real complex biological problems, their exact mathematical analysis can be very complicated or even impossible. Then the computer codes implementing algorithms from our course will often be the only way to study the behavior of a complex biological model. In this case, we will not know a priori the answer which we should expect from our model or a computer code. We will be replacing a complex biological model, which we do not fully understand, by a complex computer code. Such a computer code can give us interesting and very counterintuitive graphs, but we need some confidence that our computer code is doing what it should do. One option is to break our large code into small subsystems, which we fully understand. That is, small subsystems which we can analytically solve using methods studied in this course, like we did in our illustrative examples of the Galton board. In summary, we will see in a number of places in this course that the mathematical analysis and computer simulations complement each other. Having understood the behavior of the stochastic model, we can also start asking a question about its correctness as a description of the physical reality. Is the behavior of a particle in the Galton board really stochastic? We could use Newton's second law of motion to simulate it. I have formulated it here using a small time step delta t, because we will consider discretized version of differential equations in this course. Such an approach will be useful for two reasons. First, we will avoid some unnecessary mathematical technicalities in some places, and second, we will immediately get equations which are suitable for implementing as computer codes. A video of such a simulation is shown here. Here x is the position of the particle, v is its velocity, and g is gravitational acceleration. So these equations tell us how the position and velocity at time t plus delta t depend on the position and velocity at time t. The simulation is purely deterministic, except of a little variation which I introduce in the initial condition, because it is not possible in our experiments to place the ball at the same initial location. Our observables are again the number of particles in the corresponding containers. We observe that the ball bounces between pins, and at the end, our distribution of 10 particles is 0, 4, 1, 2, 2, and 1. In particular, we have presented a more detailed deterministic model of the Galton board, which appears to be quite stochastic. However, the deterministic model of the Galton board is much more computationally intensive than the stochastic model. So a natural question is, Why would we want to waste time by implementing the deterministic model? The answer is that the more detailed model can include a more realistic description of the underlying physical process. In fact, I had to make a choice how I describe the collisions between the ball and each pin. In my simulation, I considered elastic collisions, where the conservation of momentum and energy determines that the ball is very bouncy, like the ping ball in this video. However, this is not the case for all balls, as I am demonstrating here with this gray ball. More generally, I can introduce a coefficient of restitution, which is the ratio of the final to initial relative velocity between two objects after they collide. The previous simulation corresponded to the coefficient of restitution being equal to 1. This simulation corresponds to the coefficient of restitution being 0. That is, the ball is not bouncing at all. I use the same set of initial conditions as in the simulation on the left, but the result is different. The numbers of particles in containers are now 0, 0, 6, 4, 0, and 0. Obviously, here I am comparing two realizations of my process for alpha being 1 and 0, so the results are relatively random. A more quantitative comparison can be achieved by simulating 10,000 balls. Then the original stochastic model gave rise to predictable deterministic distribution given as the binomial distribution, which I plotted here using red lines. Simulating 10,000 balls of a detailed deterministic model, I obtained the following blue histograms. The left one is for the bouncy ball, where the coefficient of restitution is 1, while the right result was calculated for the coefficient of restitution being 0, when the ball did not bounce at all. We can see that depending on its parameters, the detailed deterministic model can lead to different stochastic models, which might lead to different deterministic models. We would need to choose alpha between 0 and 1 in the detailed deterministic model if we wanted to better match the red histogram obtained by the stochastic model. In a summary, I have introduced two, on the face of it, very different concepts, deterministic and stochastic modeling. And I have showed that the boundary between these two modeling approaches can be quite blurred. Deterministic models can appear to be quite stochastic, and stochastic models can give rise to deterministic behavior. In particular, we can construct a sequence of models with decreasing level of detail, going from a detailed deterministic model to a stochastic model, and then to the deterministic model again. Decreasing the level of detail leads to a decrease in the computational cost. And in this course, we will discuss methodologies which enable efficient simulations. At the end, we have to choose a model which includes as many details as necessary. And the choice of modeling approach will always depend on questions we want to answer. Having discussed the Galton board as our motivating example, we will conclude our introductory lecture 0 with introducing another example. This one is covered in the lecture notes and it will be studied in our course in detail. It is diffusion, Brownian motion, where we will discuss the properties of its stochastic model in chapters 3 and 4. The time evolution of one diffusing particle is shown in this video. Considering a small time step delta t, it can be described as the following evolution rule for the position of a diffusing particle. We compute its position at time t plus delta t from its position at time t by adding a small normally distributed random displacement. We can see that the trajectory of one particle is very random and fractal. Running the simulation again, this time for 5 other particles, which all start from the origin, we observed a similar behavior. The distance of the particle from the origin is controlled by the diffusion constant d, which is a parameter of this model. But the exact nature of each trajectory is stochastic and unpredictable. At the end, this simulation shows the result, which we will find later in the lecture notes as figure 3.1c. Again, the above stochastic model can give rise to deterministic behavior provided that we simulate a lot of particles. To illustrate this, we divide our domain into compartments, as it is shown in this figure, and count numbers of particles in each compartment at the end of our simulation. We have to simulate a few millions of particles, and then the results are very deterministic, as it is plotted in this figure, which gives the probabilities of a particle to be found in the corresponding compartment. It is a figure which will appear as figure 4.1b in the lecture notes, and the plotted probability density function can be obtained not only by running simulations of many particles, but also by solving a suitable partial differential equation, diffusion equation, for the spatial temporal density of particles P, which we will discuss in detail in chapter 4. Having explained that the stochastic model can give rise to deterministic behavior, we turn our attention to the underlying physical principles behind our basic stochastic model. There have been a lot of well-known mathematicians and physicists involved in studying Brownian motion. One of them was Albert Einstein. One of his famous quotes is that God does not play dice, which was his criticism of early quantum mechanics and its probabilistic background. What is behind this quote is a belief that stochastic, probabilistic modeling is just introduced to simplify the underlying physical reality, that there must be a more detailed deterministic description, like we saw in the case of the Galton board. In fact, Brownian motion of a large particle is a result of collisions with many small particles, and therefore we could use Newton's laws of motion to simulate it. We will discuss such detailed deterministic models of Brownian motion in chapter 8 of the lecture notes. A video of such a simulation is shown here, where the large particle is described by its position, velocity, mass, and radius, and we again write Newton's second law in a discretized form using a small time step delta t. This large particle collides with small blue point particles. All particles are just going straight, as you can see if you focus on one specific blue particle. It just goes straight. It only changes its direction if it collides with a large particle, where collisions are solved using the conservation of momentum and energy. We can see that the deterministic model appears to be quite stochastic, and we will discuss it in detail in chapter 8. To summarize our initial lecture 0, we used two examples, the Galton board and Brownian motion, and we discussed a sequence of models. A detailed deterministic model was possible to be described by a stochastic model, which could in turn give us some predictable deterministic information. Going from left to right, we decrease the level of model detail, which leads to a decrease in the computational cost. We will be interested in this course not only to write and analyze stochastic models, but also to end up with efficient computer codes. There is no advantage to add unnecessary details into our modeling if it makes computer simulations very slow or even impossible. So we have to choose a model which includes as many details as necessary. And this initial lecture provides us with some insights into our course philosophy. Starting with our next lecture, which I will call Lecture 1, we will go through the course material in detail, starting at the beginning of Chapter 1 of the lecture notes. Chapter 1 is about stochastic modeling of chemical reactions. It is about modeling spatially homogeneous systems, like well-mixed chemical reactors. In particular, we will be describing the state of the system by numbers of molecules of the corresponding chemical species as a function of time. There will be no spatial variation. Our goal will be to introduce these stochastic models and understand their average predictable behavior by analyzing suitable equations or by developing an algorithm to simulate such systems on a computer. We will be interested to compare stochastic and deterministic modeling. Later, in Chapter 6, we will also introduce spatio-temporal modeling, stochastic reaction diffusion modeling of such systems. Thank you very much for listening to our Lecture 0. I look forward to continuing in Lecture 1 of Oxford course on stochastic modeling of biological processes. Bye bye!